Swayam Prabha. Digital India. Educated India.
The next two theorems I will consider will be important for representation of a complicated circuit in simple terms. Okay. And these are used very widely. It is called Thevenin'S theorem, named after the person who originally proposed it. Let us say you have a circuit with a number of independent sources and linear components. Linear components of course mean linear controlled sources plus linear resistors. Okay. Basically, the controlled sources and resistors we have considered so far. Now, one restriction is that the controlled sources be controlled by quantities inside this block. Okay. Let me call this N. The controlling quantity, whether it is voltage or current, is inside this network N, and we have two terminals available to us. Okay. Let me call this 1 and 1 prime. Okay. Now, this is a common scenario. I mean, there are many cases where this happens. It could be a power supply where inside the power supply there is a complicated circuit, but you have two terminals available to you, positive and negative. Okay. Or an amplifier, or many cases where there is a complicated circuit, but you can only make connections to the circuit. You cannot modify the insides of the circuit, and it is also very common to have just a pair of terminals, two terminals. Okay. Now, in these cases, to the person who is using this circuit, who cannot make modifications to the inside of the circuit, it does not matter what the inside details are. There is no point giving them the complete schematic of the circuit. Okay. What is more useful is to give a model of the circuit, okay, a simplified model, which I will discuss shortly, so that they can make calculations using that. What do I mean by a simple model that is useful? It means that, let us say as a user, I could be connecting any other circuit to it. What I mean by a model or an equivalent of this is the following. First of all, it should be simpler, otherwise I could give the whole circuit anyway, but it also has two terminals, and let us say I connect the same circuit, this whatever my circuit is, to this thing. Okay. I connect my circuit to this, then the model should be such that whether I connect my circuit to this complete circuit or to my model, it behaves in exactly the same way. In particular, there was some voltage V 1 across this and some current I 1 going through it when I connect it to the actual circuit. The voltage when I connect it to the model should be V 1 and the current should be I 1. Okay. Then this is a useful model, and this should hold true regardless of what circuit I connect. Okay. Then instead of specifying the complicated circuit to somebody else, let us say your customer, you specify only the model. Okay. So, what we are going to do now is to derive such a model. To do that, to derive a model of the circuit that I have, circuit N, first I will use the substitution theorem. This is why I discussed it earlier. Okay. What I will do is, I will substitute this entire thing with a current source. Okay. So, let me copy over the network N, which I am interested to model, and I know we have already discussed it earlier that this circuit, whatever I connect to it, if it happens to draw a current I 1 or have a voltage drop across it, which is V 1, I can replace it by that current. Okay. Keep in mind that this is just a step in the derivation of the model. We do not need to know the value of this I 1 to make this model. Okay. So, what I am trying to do is to not deal with some arbitrary circuit, but a single current source I 1, and then I will show that whatever the value of I 1 is, the model I derive will be equivalent to the original circuit. Okay. So, hopefully, there is no doubt about the equivalence of this, because we have discussed the substitution theorem extensively, we have proved it earlier. Okay. Now, if I substitute it with I 1, I expect that there is a voltage V 1 over there. Okay. Now, let us see the relationship between V 1 and I 1 and what comes out. Let us say I was given the circuit for analysis and I had to find the value of V 1. Okay. What are the possibilities? One possibility is to use superposition. Okay. So, I will think of this as a superposition of two cases. Let me copy this over twice. Okay. This is my circuit and I think of this as the superposition of these two cases. I will mention exactly what the cases are in a moment. In the first case, I will set I 1 to 0. Okay, that is, I open circuit this one. This corresponds to I 1 being 0, and the independent sources inside the circuit, these are all active. Okay. Then the other cases, I consider only I 1 to be active, and the independent sources in the circuit are all set to 0. So, this is known as deactivating or nulling the independent sources. It is most important to keep in mind that I am nulling only the independent sources, not the control sources, right. The control sources and their controlling quantities remain exactly where they are, okay, and how they are. Only the independent sources are nulled. Okay. So, this case is clearly a superposition of these two cases, because in this case we have I 1 and also the independent sources inside the circuit, and I think of it as superposition of when I 1 is 0 here and when all the independent sources in the circuit are 0. Okay. This is the reason I discussed the minor extension to the superposition theorem earlier. Okay. Now, let us look at these two cases one by one. This is the case with I 1 equal to 0. Remember, in this case, I am analyzing only this circuit, right. I am not analyzing what is connected to it. This is what makes the derivation independent of the circuit I connect it to. Although, in the intermediate steps, I assume some circuit and that it draws a certain current I 1 and so on. What I am modeling is only this circuit and it is independent of what circuit it is connected to. So, what am I measuring here? I have this circuit N with two terminals exposed, 1 and 1 prime, and I 1 equal to 0. Okay. And let me call this voltage VTH. I will explain the terminology later. Basically, what is VTH? It is the voltage between 1 and 1 prime with the specified polarity. Of course, when you specify a voltage, you also specify the polarity. Okay. You have an open circuit between 1 and 1 prime, that is, you can think of it as an open circuit load, it is not loaded at all. Okay. And then measure the voltage across this with the independent sources in the circuit being active. This VTH is also known as the open circuit voltage for obvious reasons. It is measured with an open circuit at the output, which is an open circuit, or the Thevenin voltage in relation to this theorem. Okay. So, you will get some value, right. All you do is you take your circuit and you do not connect anything between the terminals 1 and 1 prime, where you are trying to find the equivalent and find the open circuit voltage across those terminals. Okay. Now, in the second case, okay, only I1 is active and the independent sources in the circuit are nulled. Okay. And I have this current I1, and what is V1? We have earlier discussed this. Remember now, with the independent sources nulled, this is a completely linear circuit. Okay. With the independent sources set to 0. Now, we know that this voltage V1 here in this case, V1 with the independent sources nulled will simply be proportional to I1, okay, right, because in earlier lessons and assignments you have solved problems of this type, where you are asked, you are given a circuit and two terminals are exposed and you are asked to find out what the circuit looks like. And if the circuit is linear, that is, it consists of only resistors and control sources, then looking in here, what it looks like is a resistor of some value, okay, some equivalent resistance, I will call it Req. Okay. So, if you take a linear circuit and look at it between two terminals, when I say look at it, you plot the IV characteristic, what you get is the IV characteristic of a resistor. Now, because you can have control sources inside, this resistance need not always be positive, but it will always be a resistor. All that is saying is that this V1 will be proportional to I1. Now, exactly what is it? If you look at the direction of I1, it is being pulled from this, whereas V1 is measured with this terminal being positive. So, now when you want to measure the equivalent resistance of a particular circuit, what do you do? You connect a test voltage, let us say with this polarity, and measure the current flowing in, okay, and the equivalent resistance is given by V test by I test. Okay. Now, if you observe this, V is in the same polarity as this, but I1 is in the opposite polarity, it is being pulled out. So, R equivalent will appear with a negative sign. Okay. V1 with the independent sources nulled, okay, this is the nulled source that I am referring to, will be minus some resistance times I1, okay, where RTH is the resistance looking back into the circuit. RTH is the resistance looking into the circuit with independent sources set to 0, that is by nulling the independent sources. Again, just to ensure that you understand the reason for this negative sign, let me take this circuit. Okay. And I have nulled the independent sources. How would I measure the resistance looking at the circuit between 1 and 1 prime? I would apply V test like this and measure I test, or I would apply I test and measure V test. Okay. If you compare this picture to what we had earlier, the voltage is in the same polarity, but the current is in the opposite polarity. Okay. So, that is why you get this minus R t h times I 1, right, because in this case you know that V test is R t h times I test, where R t h is the equivalent resistance of the circuit looking back that way. Now, another thing I want to point out here is that, again, although I started with some specific circuit connected to it, what I am measuring here only belongs to the circuit N. Okay. So, finally, I am modeling only the circuit N. Okay. So, we have this case where the independent sources in the circuit are null, and we have this case where I 1 is 0, meaning we are measuring the voltage with an open circuit. Okay. So, combining these two, what do we get? So, this my original case is a superposition of these two cases, and we saw that the voltage here in this case is nothing but V t h, the open circuit or Thevenin voltage, and the voltage here is nothing but minus I 1 times R t h, where R t h is the resistance looking into the circuit at those two terminals. So, clearly this V 1 here is a superposition of these two, which says that it is V t h minus I 1 times R t h. Okay. Now, this is true regardless of the value of I 1, because V t h and I t h are simply properties of N. Okay. So, to emphasize that, let me show that V t h and R t h both are properties of N. Okay. Now, what use is all this? The point is the following. The question is, can we come up with a simpler circuit which gives the same voltage when I 1 is connected to it? Okay. And it looks like it is very easy, right. If I have a voltage source V t h and a resistance of value R t h, okay, and let us say I connect this current source I 1, which by the way represents whatever circuit I connect to my original circuit. Clearly, the current flowing here is I 1 and the voltage here is V 1 equals V t h minus I 1 times R t h. Okay. So, a series combination of V t h and R t h will model this circuit. The only condition is this circuit should have only independent sources and linear components. Why linear components? Because we use superposition in the derivation of this, which is valid only for linear circuits. Okay. So, as long as this circuit has only independent sources and linear components, it can be modeled exactly by these two quantities V t h and R t h, where V t h is the open circuit voltage of this at the terminals 1 and 1 prime. Let me also mark the terminals, this is 1 and this is 1 prime, and the equivalence holds only at these two terminals, okay, for nothing else. It holds for the voltage across these two terminals and the current flowing out through these terminals. Okay. So, this simple model here is equivalent to this circuit however complicated it is. Okay. And this is known as Thevenin's theorem. So, very useful, because you could have however complicated circuit you want with hundreds of resistors and control sources, or even thousands and millions, it does not matter. As long as you are concerned only about the behavior of the circuit at these two terminals 1 and 1 prime, we can model it with a single voltage source and a single resistance. And I also showed how to determine the voltage source and the resistance values. The voltage source value is nothing but the voltage that you see across the terminals 1 and 1 prime with an open circuit between them, and the resistance is nothing but the resistance you see between the terminals 1 and 1 prime after nulling all the independent sources in the circuit. Okay. So, Thevenin's theorem says that any circuit with independent sources, which means independent voltage sources or current sources, and linear components, that is resistors and controlled sources, can be modeled at some two terminals. The two terminals will be given to you by a series combination of a voltage source of value VTH and a resistance RTH. Okay. And the series combination VTH and RTH between 1 and 1 prime, this is known as the Thevenin equivalent of N. Okay. So, that is Thevenin's theorem, and you have the Thevenin equivalent or Thevenin's equivalent of your circuit N. Okay. And this is how you determine the value of VTH. You place an open circuit between 1 and 1 prime, measure the voltage that develops here. Always mind the polarities. Here I am measuring with 1 being positive and 1 minus being negative. That is how I am measuring the voltage, and that is how we have to place it in the equivalent as well. And this is how you measure the resistance. You deactivate all the independent sources. You will be left with only linear components, that is resistors and control sources. Then looking back into the circuit between terminals 1 and 1 prime, you determine the resistance RTH. Okay. So, these two together will give you the equivalent of N. Okay. So, clearly you can see that this is a much simpler model than the original circuit, which could have hundreds or thousands or any number of components. Okay. So, that is the reason it is used so widely.